Hello, Kai, everybody. I am Pascal Elahi from the Pawsey Supercomputing Research Center, and I will be presenting today how to install GPU software. So installing and developing GPU software on Setonix for those who are migrating from Topaz to Setonix. So the focus of this training, there are several main learning outcomes, and the target audience is all Topaz users. It might seem like it's more for developers, but it is really for all users, and I will discuss why that is the case. So the learning outcomes are to learn about GPU programming models, such as ROCm and HIP, to learn about GPU offloading technologies, such as OpenMP and OpenACC, be familiar with the best practices of installing GPU-enabled software on Setonix, and to be aware of the development tools that exist on Setonix. So compilers, debuggers, profiles, and the ability to port code. All right, so let's dive into the GPU programming technologies. So the main basis of Setonix is AMD GPUs, and because of the transition from NVIDIA to AMD GPUs, there's a transition of GPU technologies. And the main one is the ROCm platform. So ROCm is the GPU software development and runtime environment provided by AMD. On NVIDIA GPUs, such as was on Topaz, it would have been the equivalent of CUDA. So CUDA is there, and here we have ROCm. On Setonix, ROCm is available through a module, so you can load that module. And what it does is it provides quite a large set of tools and essentially libraries and drivers. So there is the HIP. One of the main ones is HIP, which is a C++ language extension and API calls, which is equivalent to CUDA. And so there's also an equivalent compiler, HIPCC, that matches NVCC. There's GPU-enabled numerical libraries, such as ROCFFT, ROCBLAST, and ROCRAND, which are similar to the CUDA equivalents of cuBLAST, cuFTT, and so on. There are debugging and profiling tools, such as ROCgdb, ROCprof, and ROCtracer. And there's also HIPIFY tools. These are meant to allow porting of CUDA code to HIP. They're HIPIFY Perl and HIPIFY Clang to help port CUDA codes. All of these sort of sit on top of the ROCm runtime. And we not only have one ROCm version on Setonix, we actually have two. There's an additional one, which is 5.4.3, a later version, but it's an experimental installation. And there will be a mix of versions of ROCm available on Setonix as you go forward, but we will definitely indicate which one is stable and which one is development. So to dive in, I mentioned HIP. HIP is the programming language. It's the heterogeneous interface for portability that has been developed by AMD to help program on AMD GPUs. It is a C++ language extension, and the runtime API is very similar to CUDA. For obvious reasons, it makes it also easy to transition from CUDA to HIP and ROCm as a base. Code written in HIP can be compiled with HIPCC, the compiler driver, and run on either NVIDIA or AMD hardware. So in this case, HIP actually is a high-level interface that can either point to CUDA calls or point to the ROCm runtime environment and ROCm drivers. So then once you HIPify code, it does not mean that you're bound to solely AMD. You can also still run it on an NVIDIA system, so long as there's a HIP interface provided to point to the correct CUDA. HIP provides HIPify a tool to translate CUDA codes to HIP, and then although these tools do not work in all instances, this is a really good starting point. I will discuss porting codes later on in this presentation. On AMD platforms, an AMD fork of LLVM is used. So this is the C++ backend. As I mentioned, on NVIDIA platforms, HIP is a wrapper around CUDA and then everything that CUDA provides. For more information, we do have actual documentation as well. So those are the sort of CUDA equivalent, sort of explicit programming of GPUs, but there's also OpenMP. So OpenMP is an API designed to provide parallelism on shared memory systems, but also does offloading to accelerators like GPUs. The API supports C, C++, and Fortran programming languages. You can find more information at Pawsey as well about OpenMP programming. And now the CPU parallelism, so OpenMP, as I said, does both GPU and CPU. And the CPU parallelism is actually supported on all Cray programming environments and is also supported on HIPCC provided by the ROCm 5.0.2 module. The GPU offloading is currently available on C++ for HIPCC through the ROCm 5.0.2, and also through the compiler wrappers that are provided by the Cray programming environment. which is slightly different from Topaz. They essentially provide Fortran, C, and C++. That's the lowercase cc is the equivalent of a C compiler. Uppercase cc is the C++ compiler, and FTN is the Fortran compiler, and it's provided by the programming Cray environment. So specifically, the Cray compilers provide offloading through OpenMP to GPUs. The C++ HIPCC provided by ROCm 5.4.3, I mean, in principle, could provide OpenMP offloading to GPUs, but currently it's not supported. There are issues in the current deployment for offloading by OpenMP. OpenACC. So OpenACC is a very similar pragma-based directive. It's a API parallel programming standard for open accelerators, essentially facilitating programming on heterogeneous CPU and GPU systems. And OpenACC supports both C, C++, and Fortran programming environments. And you can find more details of the standard on their website. Now, GPU offloading is only currently available through the Fortran FTN compiler provided by the programming environment of the Cray compilers. GNU compilers on Setonix do not support OpenMP offloading, so they, in principle, would support it. But the ones on Setonix currently do not actually talk to GPUs. They're issues that we are currently working on. So this would be for Fortran codes, really only on Setonix right now. Now, installing GPU-enabled software on Setonix. So to give context, the software stack on the Setonix for GPUs is an evolving setup. Now, GPU-enabled software, typically we would use Spack. So Pawsey recommends Spack, this package manager, via the Spack module to install CPU software. And that can be found, the information on that can be found in our documentation. However, the GPU accelerated software with the current deployment of Spack is not well supported. We are in the process of working on the next software stack deployment with a newer version of Spack that would also enable GPU-enabled, would allow us to install GPU-enabled software and would allow also users to install GPU-enabled software. This is going to happen in the future. We do have GPU-enabled containers as modules on Setonix. So these essentially are, they just look like modules as you would normally them with module load, but they actually point to a container. And I will mention container technologies later, but the idea is that you have a module that would provide you access to certain software like GROMACS, like Labs, CP2K, and NAMD. However, these containers are still in early testing phases and not recommended for production use yet, principally because there's a couple of caveats. The containers can only currently scale up to one node. So one node on Setonix on a GPU, on the GPU partition consists of 64 cores of essentially a Zen 3 AMD CPU, as well as 8 GPUs. And the containers can only currently scale up to one node, so 8 GPUs and 64 cores. And some containers themselves also have limitations for a single GPU. That is not all containers here. And you can try these containers and see if they work. They should all work with 8 GPUs. But if you encounter other containers as modules, there might be limitations. Additional containers and modules can be installed through using the SHPC package manager. So this is a tool designed to essentially install containers as modules. So they look like modules to a user, and they provide an interface such that all the normal commands you would use with that package would be available. So you can load this module and install software via this module, as an example from below, where we are essentially using SHPC to install a local copy of GROMACS. For more information, you can visit our documentation. Now that was GPU-enabled containers as modules. You can also explicitly use containers. So the AMD Infinity Hub, AMD has been working to transition software from CUDA to HIP. And so they've developed GPU containers for some specific scientific software, AI, and machine learning applications. Popular software containers are OpenFOAM, GROMACS, LAMPS, NAMD, and Amber. So there's a larger list, as well as the E4S initiative, which provides containerized build tools and applications for HPC. And both sites are listed there, where you can visit and see what is available. Now, the idea of a container is that you can use the Singularity container engine that's provided on Setonix to then pull this container and use this container. as is if it was essentially a fully enclosed software stack, providing you access to, in this example, GROMACS. So the idea is I have loaded Singularity. I then use Singularity to pull a container and then use that container. Now, again, these containers are also still probably not ready for production use, and they have similar caveats to the containers as modules. For a full discussion of containers, that's beyond the scope of this presentation, but there we have documentation discussing containers, what they are exactly, and how to use them with the Singularity container engine. And feel free to contact us if you want to use some of the containers that are available through AMD that are not provided as containers as modules, in case you run into any issues kind of using a container or run into any limitations of the container. Now, there's also GPU-enabled modules. So this is essentially the ever-evolving setup that we are having for bare metal builds, essentially optimized builds for the Setonix GPU system. And the naming convention is essentially software under -AMD-GFX 990A. The -GFX refers to the driver for the GPU, and AMD just the fact that we have AMD GPUs. The modules can be loaded as you would. They can be seen on both CPU and GPU nodes. So if you go on to the login nodes of Setonix and do module avail and search for the keyword GFX 90A, you will see some software presented as custom builds. They're custom bare metal builds, so they should be optimized for the Setonix supercomputer, and they'll run on GPU nodes. Now that's essentially the process we have of available software, but that might not satisfy all researchers. There might be software that is not available as a module, and this is where it becomes manual installation. And so as we discuss manual installation, it's a good idea to discuss navigating the manual installation process, because the manual installation process is perhaps a bit more complex than it would otherwise normally be, and is dependent on what the code is designed to do. So there are different approaches for compiling MPI-enabled codes. So that's MPI distributed node codes, HIP-enabled codes, so codes that are already HIP, you make use of HIP, and OpenMP-enabled codes. And that's true even for OpenACC. CUDA-enabled codes require an additional step of porting to HIP before compilation. And it's true that not all GPU technologies, I didn't mention all of them, right? So not all of them are fully supported, specifically also for even C++. So there's OpenCL, SYCL, there's a couple other ones as well. But it's possible that there are workarounds for the software stack that you're trying to deploy. Now, if we look at the figure, right, this flow chart for deciding how to compile software, the first high-level question you need to ask yourself is whether the software you're using is MPI enabled. So if you couldn't find a module for it and you wanted to build a version, there's a different set of steps that need to be undertaken if you have MPI-enabled software that would use MPI and possibly go across nodes. If that's not the case, then you can ask yourself, was it HIP-enabled? Is it CUDA-enabled? Because if it's CUDA-enabled, you can port CUDA code to HIP. That may itself be a bit of a complex process, but it is definitely a process which we're very willing to help with, and there is documentation out there as well, and tools as well. Then it becomes pragma directives. So pragma directives like OpenMP and OpenACC do not need explicit porting. So if you have these codes that are essentially use OpenMP or OpenACC to offload, it's possible there may not be any sort of explicit porting required, but there are steps to take, particularly to do with compilation flags. OpenACC enabled Fortran codes. If you have an OpenACC enabled Fortran code, then it's a matter of compiling with the appropriate flags. And if you do have an OpenACC code, but it's not Fortran enabled, they'll require some thought and maybe a transition process. So please contact the help desk. And if you have any points in this process, please contact the help desk. We are very eager to help transition to the new AMD GPUs. Now, getting started with manual installation. So at early access, Pawsey provided GPU-enabled software is limited, right? We are still dealing with issues with moving the new software stack to the new package manager, which will better support the GPUs. And there's also the simple fact that the AMD GPUs, some software is still transitioning to make use of the AMD GPUs. So the software stack that's truly GPU-enabled, it will grow and will evolve. We'll, of course, discuss this and mention this as it increases and there's better support. And this is one of the reasons why we're asking all Topaz users to have a look at this manual installation process in case the software that they are using, would like to use, is not currently available through the modules. The first main steps in a manual build is to check that the code is HIP-enabled and compatible with AMD GPUs, is either C, C++ Fortran is OpenMP offloading, or is Fortran and uses OpenACC offloading, because those are the ones that are supported. So the first step is to log into a GPU node and load the appropriate modules. So you have SLLock. Here I've asked for one node. I've asked specifically for the partition of the GPU development environment, and I've asked for one GPU, and I've made sure that I've asked for set the account to be the project account dash GPU to get access to the GPU partition. We then swap the default programming environment. So on all other compute nodes, the default programming is to make use of the GNU compiler family. And for directive beta offloading, that's still not fully enabled. So we suggest moving to the Cray compiler environment, programming environment. Then we load the ROCm module. So the ROCm provides that runtime basis and all the drivers that we were interested in. I've put in here version because you can make use of 5.0.2, and that's our standard recommendation, but it's possible that 5.4.3 might offer something that you're interested in. And then to load the Cray programming environment accelerator module, so this excel-amd-gfx90a, which just ensures that certain compilation flags are set as well as appropriate drivers are in the path. The idea of having a GPU node while you're doing the compilation is simply because the GPU driver is present. So you have a GPU, which you could offload, and if the compilation process involves a unit test or some other sort of small compilation of a GPU code that then needs to run on the GPU, you will have a GPU available, and so the test will not fail. Now, for general guidelines for compiling software, we do have documentation to discuss just how to manually build software in general, regardless of whether it's CPU or GPU. Here, we're focused on the specific steps for GPUs. So the manual installation of non-MPI software with HIP. So the idea would be, I don't have MPI software, and I have HIP-enabled code already. So the pure HIP code requires the HIPCC compiler, provided by the ROCm module. And once on a GPU node, you can simply invoke HIPCC, compile the source code, and it will produce an executable or produce object files as desired. OpenMP offloading can be compiled on a GPU node with ROCm 5.0.2 specifically, that specific version. And in there, the compilation process requires extra flags. So I've listed all the flags to be quite verbose, which is an offload to the architecture. So with GFX98 is the driver or the architecture for the MI250Xs that we have on Setonix. Then you provide the OpenMP flag, so that's FOpenMP. And you can then indicate the targets and also the architecture. So in this case, there's like MARCH GFX908. You provide the source code and the output. And the reason I've been extra verbose in HIPCC doesn't necessarily need to provide all these flags, but HIPCC basically uses the Clang CC++ compiler in the backend, which is also provided by the ROCm module. It can also do OpenMP offloading, but it needs the extra flags and some additional flags for appropriate ROCm libraries. And the reason this might be useful is if you want to deal explicitly with the Clang compiler so you can be a bit more explicit of what's going on, you kind of know the steps you need to do for getting the offloading for OpenMP. Now MPI. So MPI-enabled software, right, is software where you're going to make use of the MPI programming API and programming, but also want to do sort of multi-node compute. So there are several steps. One is to make sure that the MPI, the Cray MPI libraries, binaries, libraries, etc., are all in the paths that are automatically looked for. So there is path, C path, and LD library path that need updates. You can then compile any HIP-enabled source code that doesn't have any MPI, just with HIPCC. So you compile and you generate an object file. And you can also compile any OpenMP source codes with the Cray programming environment. So here I have cc-f-OpenMP for C. It happens to be C++, but that would also apply for C. For the Fortran compiler provided by Cray, it has a different set of flags. So to enable OpenMP, it's -HOMP. And then you would have object files that essentially allow OpenMP offloading. And then you compile the overall any MPI-enabled code, so code that contains MPI calls, with the the Cray provided compiler wrapper, so they automatically add a bunch of flags, but it's good to do the export beforehand. And you also need to specify that the HIP platform is compiled specifically for AMD, and then you can construct your final executable. And so it's a multi-step process. And if you have code that has a mix of everything, then it's a matter of sort of deciding the optimal path. And you might have to use the HIPCC compiler everywhere, because HIPCC can do the explicit interpretation of any HIP code. And that is the next slide. So if you want to do a manual installation of HIP-enabled software with the HIP compiler only, again, you need to set the environment paths. You can compile HIP MPI code, right? In this case, because we set the environment paths, it should be able to handle the MPI code, but you will at the end need to add some extra libraries. So the offloading looks very similar to the previous offloading for HIP. The final step, though, has HIPCC as opposed to the Cray compiler wrappers, such as CC or FTN. And there's an explicit linking to the MPI library with the -L MPI, and that should generate an MPI-enabled HIP code. Now, all of the previous two slides have focused on MPI, but I should mention that MPI, this message passing interface that allows CPUs to communicate across the network, also allows GPUs to communicate across the network. We do have MPI that it can do GPU to GPU communication. So that's straight GPU to GPU communication, but that requires extra steps. So GPU to GPU MPI-enabled software, you're better off using the HIP compiler. And there's just several extra steps, not a huge number of steps. One, you have to set an environment variable to indicate that you want GPU support enabled. By default, MPI code, compiled MPI code is not enabling GPU to GPU communication. It's focused on CPU to CPU communication. Enabling GPU to GPU communication does not disable CPU to CPU communication. So you're just adding an extra bit of support, but extra flags have to be added. And that's where I've highlighted these specifically, including a library path, as well as adding a -LMPI GTL HSA. So this is the MPI portion that does the GPU to GPU communication. And then you should have a code that can run with GPU to GPU communication. But to run as well, you may need to make sure that you set this environment variable, the mph_GPU_ support enabled. That's required for both compiling and running the software. So that is all the, if you will, heavy focus on HIP, or the equivalent of CUDA compilation. You can also do a manual installation of Fortran-based OpenACC software. It may look simplistic, but it's a smaller set of software that's fully supported in this fashion, which is to compile the OpenACC code with the Fortran compiler wrapper. So the Fortran compiler wrapper will add all the appropriate flags, and just needs to be told that it's going to compile with the OpenACC by compiling with the -H ACC flag. This will enable MPI-enabled code. Now, to do GPU to GPU communication, you'll still have to do the previous steps. That is required for any sort of MPI-enabled GPU to GPU communication. So that's manual installation. That's not the only way you might manually want to install software. So we might provide a module, but it's possible that that module is not making use of what you would like to use in terms of GPU-enabled libraries. Some codes make use, for instance, of BLAS. So this is linear algebra. It's a standard pack. And it's possible that the ROCm environment will provide an ideal GPU calculation of BLAS. So ROCm provides several of these. This is not the fully extensive list, but there's FFT, BLAS, random numbers, and solver, which is LAPACK, which should be accessed through the HIP wrappers. So HIP FFT, HIP BLAS, and HIP rand and HIP solve provide wrappers around these ROCm libraries. And to then compile the source code, you just have to add the appropriate flag. So HIPCC-L, HIP FFT, HIP BLAS, and HIP solver would give you the equivalent of a code where the library itself that's being called is GPU enabled. For CUDA codes that use such libraries, such as QFFT, it requires porting to HIP. And an example in that case would be to take QHIPFFT_plan_create. This is literally in the source code. So this particular string that calls this function name now becomes HIPFFT plan create. Otherwise, the code is unchanged. Now, things to be aware of when you're compiling from source. So build systems. Not all build systems have been updated to best make use of discovering ROCm environments and HIP. So CMake, which is a build system that's used by a large number of software, older versions of CMake cannot auto-detect HIP. They don't have any in-place code to kind of deal with the fact that you want to compile with HIP as opposed to CUDA. But the current module that we have available, which is 3.2.21.4 on the Setonix system, is able to do this. There is a system CMake. We suggest to not use that system CMake. You make sure that you use the module that's provided. And also the source code may require an update to the CMake's list file. So this file the CMake uses to kind of dictate how the build configuration process should behave so that it can build the software might require some updates for some source code. The subtle one here for things to remember is libraries. So the default behavior on HP Cray systems, and that's XE systems as well, but that's all Cray systems, is that math libraries such as BLAS and LAPACK were provided through the Cray libsci module, and that was automatically always loaded when using the compiler wrapper. So by default, if you look at when you log into Setonix, you'll notice that Cray libsci is a default module. That's quite different from Topaz, where the math libraries, you'd have to explicitly load the appropriate math libraries. Here, by default, they're already loaded, and this may not be desirable. And it's because the Cray libsci module is still not fully supporting GPU offloading, and so you may want to be a bit more explicit and unload that module, and then load the modules that you want to provide. So if you unload Cray libsci and you had ROCm loaded, and then you can make sure that when you compile a code, it would complain, let's say, with the absence of a BLAS library, and you'd have to explicitly load HIP BLAS. And so it'd be maybe easier to handle the library calls because you'd be a bit more explicit as to what libraries are being loaded from where. Now, developer tools. So we've discussed installation processes, but it might seem a bit daunting to transition from CUDA to HIP or trying to deal with any issues you encounter in compiling. There are several developer tools. So the big one that people might make use of when manual installation might be porting CUDA code to HIP. So porting CUDA code with HIPIFY. So there's two versions of HIPIFY. One is HIPIFY Perl, which is a conversion script that will map CUDA calls to the corresponding HIP call. It's quite a good job for most of the CUDA stack, but there's some things that it won't necessarily translate. So specifically the math libraries that CUDA has developed, that HIP has also developed, that mapping might require you an explicit manual change of the code. HipClang is like HIP Perl, but it also has a compiler, so it not only converts but tries compiling it. So it's and it can deal a bit better with some edge cases, but then it might hide issues of what it's trying to do. So do the non-trivial process of porting codes. We really suggest HIPIFY Perl to begin the process, and then you do an explicit compilation with HipCC. It might make it easier to determine what is being done. And so here's an example where I've loaded the ROCm module, I HIPIFY Perl the original CUDA code, and then I pipe it to a new file that also has the .cu as the suffix, and then compile that code. It's quite likely that porting code will require more modifications, particularly to get optimal performance on AMD GPUs, and in some senses might be incomplete. As I mentioned, that the HIPIFY tool might not be aware of all CUDA calls and that have an equivalent HIP call, specifically as some of the math libraries are in flux and are still in development. There's some porting examples available through AMD, so you can have a look at that. And please contact the help desk in case you have any questions. Debuggers and profilers, there are ways of debugging code. So ROCgdb is a command line profiler provided by AMD for AMD GPUs. It's very similar to the CPU debugger GDB, so that type of command line interface. It's provided by all versions of ROCm, and we suggest having a look at the ROCm debugger user guide, so AMD's user guide for specific ROCm GDB stuff. But even because it behaves like GDB and it's built on it, if you look at a site discussing GDB, and we also have some documentation on just GDB debugging, CPU debugging, those commands still apply. ROCprof is a command line profiling tool for AMD GPUs. The AMD site has quite a good discussion of ROCprof and how to make use of the information it provides. And these tools are just one of many. So these are debuggers and profilers, but there's other debugging tools. So Perfetto is a useful tool for visualizing profiling information provided by ROCprof. It's just a website. You can, there is actual, Perfetto does provide a process for having a local copy because the website has a limitation on how big a profiling data set you can look at. And so local copies can go beyond that 2 gig range, but typically you never need a local copy. ARM4 CDT, so this powerful MPI debugger that we have on Setonix, we've had on our systems, it currently does not support AMD GPUs, but can be used for CPU debugging. And there is a roadmap to eventually including AMD debugging. Cray provides several tools for debugging, such as the Cray CCDB, so the Cray, I can't remember the actual source, CDB, but debugger. And it's provided by the Cray CCDB module. And profiling tools like Cray Patent Map that are provided by Perf tools, which also support MPI. And it currently does not fully support AMD GPUs, but there's plans for to do so in the future. So these compilers, these Cray provided debuggers, sorry, not compilers, but debuggers and profilers that Cray provides will in the future be a way of really looking at the AMD GPUs. Just to mention, because for people who have done debugging and profiling on Topaz with NVIDIA GPUs, there's really nothing equivalent to NVIDIA Insight, right? So this is quite a useful profiling tool. It's very useful to look at how code behaves. But software is being developed to provide similar functionality for AMD GPUs. And the last points, such as we are providing additional developer tools such as OmniTrace and OmniPerf. These are tools that we are working to make sure that they behave well and are fit for production codes. Those 2 tools are essentially meant to provide NVIDIA Insight-like exploration of GPU codes. So how do I get help? Right, so it might seem a bit daunting, but if there is a partition quick guide. We have migration material, but key thing might be the help desk. So there's online material provided by AMD to look at how to use AMD GPUs, but the help desk is a good point of call if you are running into issues running software and you require a manual installation of your software. So thank you very much for listening, and I hope you have a great day.